The answer lies in heat treatment. Stick around to discover the secret superpower making steel the most versatile material in modern engineering. Steel accounts for over 90% of global metal production. Its dominance comes not just from strength and affordability, but something truly unique, the ability to be completely transformed through heat treatment. Here's what'll blow your mind. Take 3 steel parts with identical chemical composition. The first is soft and ductile, the second incredibly hard and brittle, the third strong and tough. The only difference? Heat treatment. This ability to control and fine-tune material properties through precise heating and cooling makes steel absolutely remarkable. Let's dive in and see exactly how it all works. Steel's foundation: understanding the ingredients. Steel is an alloy of iron and carbon, usually with other elements mixed in at small proportions. We classify steels based on carbon content: low carbon, medium carbon, and high carbon steels. Anything beyond 2.1% carbon is actually cast iron, not steel. If steel contains significant amounts of alloying elements above around 1%, we call it alloy steel. Otherwise, it's plain carbon steel. To understand how heat treatment can completely transform these materials, and why different carbon concentrations matter so much, we first need to look at pure iron and see how it behaves at different temperatures. How iron transforms with heat. Pure iron undergoes several dramatic changes when heated. At room temperature, iron atoms arrange themselves in a body-centered cubic form, or BCC for short. Picture one atom at each corner of a cube, with one right in the center. This structure is called ferrite. Above 912 degrees Celsius, iron becomes more stable in a completely different atomic arrangement. It undergoes a phase transformation. The atoms shift from that body-centered cubic structure to a face-centered structure, where atoms pack together more closely and efficiently. This FCC form of iron is called austenite. The ferrite to austenite transformation happens at 912 degrees. As temperature keeps climbing, iron actually changes back to ferrite at 1394 degrees, before finally melting into liquid at 1538 degrees. These different solid phases are called allotropes of iron, and engineers assign Greek letters to each one for convenience. Carbon changes everything. Now here's where things get fascinating. Let's see what happens when we add carbon to the mix. The iron-carbon phase diagram becomes our roadmap for understanding heat treatment. The amount of carbon affects transformation temperatures and introduces entirely new phases. Because carbon atoms are so small, they fit into the interstitial spaces between iron atoms, kind of like fitting marbles between basketballs. But here's the catch: the BCC structure of ferrite can only accommodate a tiny amount of carbon. It has maximum solubility of just 0.02% carbon by weight at 723 degrees, roughly 1 carbon atom for every 1,000 iron atoms, and even less at lower temperatures. When the alloy contains more carbon than ferrite can handle, excess carbon atoms form a new phase called cementite alongside the ferrite. Cementite is a hard, brittle compound made up of 1 carbon atom for every 3 iron atoms. Austenite holds much more carbon than ferrite, from 0.8% at 723 degrees up to 2.1% at 1147 degrees. That's roughly 1 carbon atom for every 10 iron atoms. Add more carbon beyond that, and you get a 2-phase material with austenite and cementite phases coexisting. The magic of perlite. For an alloy containing exactly 0.8% carbon, a sweet spot we call the eutectoid composition, something special happens. The structure remains austenite while cooling until it hits 723 degrees. At this precise temperature, austenite transforms from FCC to BCC structure, and excess carbon combines with iron atoms to form cementite. These 2 phases form a distinctive microstructure with alternating layers of ferrite and cementite, which we call perlite. This is special because austenite transforms entirely and simultaneously into ferrite and cementite, producing only perlite. In steels with less carbon, hypoeutectoid steels, some ferrite forms before reaching the eutectoid temperature. The final microstructure becomes a mix of pereutectoid ferrite and perlite. In steels with more carbon, hypereutectoid steels, cementite forms first as austenite cools. At the eutectoid temperature, remaining austenite transforms into perlite, creating a mix of pereutectoid cementite and perlite. Time and temperature, the TTT diagram. All these transformations rely on diffusion, the movement of carbon and iron atoms through the lattice to form new phases. Because diffusion takes time, the iron-carbon phase diagram only represents equilibrium conditions. It assumes cooling and heating occur slowly enough for atoms to fully rearrange into their most stable phases. In reality, it can take minutes, hours, or even days for austenite to fully transform into ferrite, depending on composition and temperature. This is where TTT diagrams, time-temperature transformation diagrams, come into play. They map out the relationship between time, temperature, and the phases that form in a given steel. The diagram shows how long transformation will take if steel is cooled to and held at a constant temperature. For example, if you cool eutectoid steel to 500 degrees and hold it there, austenite will start transforming into ferrite and cementite in less than a second, completing the transformation after about 9 seconds. The game changer, martensite. This is where things get incredibly interesting, because the TTT diagram reveals non-equilibrium phases that play a central role in heat treatment. The most important is martensite. Martensite forms when austenite cools so rapidly that carbon atoms don't have time to diffuse out of the FCC structure to form cementite. The FCC lattice wants to transform to BCC, but can't because of trapped carbon atoms. So it distorts into a new body-centered tetragonal structure instead, martensite. This BCT lattice forms almost instantly, growing from austenite grain boundaries and propagating at close to the speed of sound. This happens incredibly fast because the transformation is diffusionless. Unlike other phase transformations, it occurs without any long-range motion of atoms. The result is a microstructure of long, thin plates of martensite slicing through the prior austenite grains. The distorted lattice of martensite makes it extremely hard and strong, but also very brittle. This is due to trapped carbon atoms, which strain the lattice, locking the structure in place and blocking the motion of dislocations. Steel's carbon content has huge impact here. More carbon means greater lattice distortion, which increases hardness and strength at the cost of increased brittleness. Real-world cooling, the CCT diagram. In practice, steels aren't usually cooled to a fixed temperature and held there. More often, they're cooled continuously down to room temperature. The phase transformations occurring with these more realistic cooling conditions are shown on a CCT diagram, continuous cooling transformation diagram. This is similar to the TTT diagram, except each curve represents a different linear cooling rate. Cool a 1080 steel from 800 degrees Celsius at 200 degrees per second and you'll get martensite. At 50 degrees per second, you'll get a mixture of perlite and martensite. And at 10 degrees per second, you'll get 100% perlite. The CCT diagram shows how challenging it can be to obtain martensite. Plain carbon steels often require very high cooling rates that aren't achievable in practice with large parts. This is one main reason we add alloying elements like nickel and manganese to steel. They shift the CCT curves to the right, allowing martensite to form at slower, more practical cooling rates. Heat treatment processes, putting theory into practice. Now we can finally get to heat treatment itself, which is all about using careful heating and cooling to manipulate the microstructure of steel parts and obtain useful or improved material properties. Let's break down the 4 key processes. Annealing makes steel soft, ductile, and easy to work with. It's often applied after forging or casting to relieve stresses and make the part easy to machine. The process involves heating steel into the austenite region, then cooling very slowly inside the furnace. Because cooling is so gradual, carbon atoms have plenty of time to rearrange into the wide ferrite and cementite layers of coarse perlite, which has low strength but is very soft and ductile. Normalizing is similar to annealing. Both heat steel into the austenite region, with normalizing using slightly higher temperature. The main difference is steel cools in air instead of slowly in the furnace. The higher temperature helps eliminate irregular microstructure left over from previous processing steps. And the faster cooling rate produces fine perlite structure that's stronger and harder than annealed steel while still retaining useful ductility. Quenching involves very rapid cooling, usually by plunging the steel part into a bath of water, oil, or other medium. The objective is to produce martensite. The quenched steel has high hardness and strength, but is far too brittle to be useful in most applications. Tempering is the follow-up process to quenching. The quenched martensite steel is reheated to temperatures between 200 to 600 degrees Celsius, below the levels needed to transform back into austenite. It's held at this constant temperature for anywhere from a few minutes to several hours before cooling. During tempering, excess carbon atoms trapped in the distorted martensite lattice diffuse out and form extremely fine particles of cementite, allowing the lattice to relax. The resulting microstructure, called tempered martensite, greatly improves ductility and toughness while retaining much of the strength and hardness. Steel in this quenched and tempered condition is usually called hardened steel. This process is used for critical parts that need high strength combined with toughness, like crankshafts, high-strength bolts, tools, or heavy-duty structural components. The challenge of hardenability. The objective of quenching is to cool material fast enough that austenite turns into martensite through the entire cross-section. This can be challenging with thick components, where the core takes longer to cool than the surface, potentially resulting in perlite or binite forming inside instead of martensite. Hardenability quantifies a steel's ability to form martensite to a given depth during quenching. A steel with good hardenability will form martensite more easily at slower cooling rates and produce martensite all the way through thick sections. The Jominy end quench test is the standard method for measuring hardenability. It involves heating a cylindrical steel sample until it's fully austenitic, then quenching one end with a standardized water spray setup. This creates a controlled cooling rate that decreases as you move up the sample. Hardness measurements are taken at regular intervals, and results are plotted as a Jominy hardness curve. Hardenability is mainly determined by composition. Maximum hardness is governed by carbon content. A 1080 steel reaches higher hardness than a 1040 steel because it contains more carbon. But the rate at which hardness decreases with distance from the quenched end is mainly influenced by alloying elements. A steel like 4340, which contains nickel, chromium, and molybdenum, has excellent hardenability and is perfect for thick parts that need to be quenched and tempered. Surface hardening, best of both worlds. Sometimes we don't want the entire component hardened. Instead, we might only need a hard, wear-resistant surface while keeping the interior tough and ductile. This is common for components like gears and shafts that experience high contact stresses but also need to resist impact loading. Surface hardening techniques create a hard outer layer while preserving the softer, more ductile core. Induction hardening and flame hardening involve directly heating the surface, followed by quenching to create a hard martensitic layer. But these methods only work on medium or high carbon steels. For low carbon steels, we use case hardening techniques that actually alter the surface composition. Carbizing involves heating the part in a carbon-rich environment to increase surface carbon content, followed by quenching. Nitriding introduces nitrogen into the surface to form hard nitride compounds without needing quenching, a big advantage for precision parts since it avoids warping that can occur with quenching. Bringing it all together. In practice, heat treatments like annealing, normalizing, quenching, and tempering are combined into sequences along with forming and machining steps. Each stage of the manufacturing process prepares the steel for the next, until the final form is obtained with a microstructure that provides the perfect balance of strength, hardness, and toughness. So there you have it, the fascinating world of steel heat treatment explained. From understanding phase diagrams to mastering the art of quenching and tempering, you now know the secrets behind one of engineering's most powerful tools. This is the kind of knowledge that separates good engineers from great ones. If you found this video helpful and want to see more deep dives into engineering and material science, hit that like button and subscribe to HowToHub. Drop a comment below and let us know what engineering topic you'd like us to tackle next. And if you're working on a project that involves heat treatment, share your experience, we'd love to hear about it. Thanks for watching, and we'll see you in the next video.